Okay, today we have only old announcements. The programming assignment is still out, and it's due September 27th. And there are now, the lecture videos are out on YouTube, so I appreciate your being here. But it's good for you to be here, that's for sure. Today's plan is to talk about a little bit more about memory model, though not very much, and then to talk about linked structures, linked lists, and maybe get to the list abstract data type. Any questions about anything? Okay. This is a picture of memory. So this is just to remind you that memory is like a big array, and every piece of data that you store in the computer and manipulate is someplace in there. It has a physical location inside of that chip. And to address it, you use memory addresses. Those are also called pointers in C++. And so what we're talking about now is about pointers and how to manipulate them in C++. So this is a small warm-up example for pointers. And maybe what I would like you to do is to go through and tell the answer to the output here. And also what the type of queue is. And so let me just let you discuss that among each other. From your understanding of what pointers are, they're memory addresses, and the operations that are performed on these pointers are dereferencing, or this sort of star operator, and the taking the address of operator. Those are the operators that are allowed on these pointers. Anyway, let me just ask if this is a reasonable task. How many people are slightly familiar with pointers? How many people are not slightly familiar with pointers and don't know what I'm asking? No? Okay, well, let's try this exercise just to see how it'll go. For those of you that are completely, just raise your hand and I'll come around and I'll talk to you. If you're very, very uncertain about what's going on. Okay, so three things. What type is Q, and what are the two output lines here? Then we'll get to the second part. Just those three things. That's it. Okay, everybody, okay. There have been a couple of questions, so that now I sort of feel bad about doing this to you. But anyway, I don't feel that bad. What type is Q? P is a type. It's a int pointer. That's what this declaration says. Int star P means that P is a pointer to an integer. The weird thing about C and the syntax of C in C++ is that this int star P comma Q, which you might think declares Q also as a pointer to an integer, does not. It declares Q to be just an integer. So, sorry, that's the way it is. Which means, if this is confusing to you, never use this feature of C++, that you can declare multiple variables on one line. You can always just declare it explicitly one per line, int star P, int star Q, int star whatever. You know, if you wanted to declare it on the same line, you'd have to stick a little star in here. If you wanted Q to be a pointer, you'd have to stick another little star in here. But don't think about that. Think about just do it one line at a time. That's probably the easiest thing to do. Okay, so that was the kind of, sadly, the kind of nitpicky question. The real questions here are what this code does and what you get when you perform this output statement. So just let me walk through a couple of these steps first, and then I'll ask what your answers were. This declares x to be an integer. So x is now a variable. It's an integer valued variable. But the value of x is stored someplace in memory. There's an address for it. And this statement here takes that address and stores it into a variable p, which is a pointer to an integer. It's a memory location. That memory location here is, whatever, some memory location. X's value is inside of this memory location. X's value is in there. X's value is inside this box. But the box has an address, something like 0x0 blah 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 7. P is that address. It's the address of the variable x. So P, that's P. All right, let me write it this way. P equals that thing, that address. And so sometimes we write it like this. P points to the box. It's a pointer to that memory location. But really what it is it's the address, okay? Then this statement, star is like a dereferencing operator. When you put a star in front of a pointer, it means give me the thing that the pointer is pointing to. And you can use that thing as an L value or an R value. What's an L value and what's an R value? This is an L value. It's on the left-hand side of an equality, which means it's getting something assigned to it. If you put it on the other side of the equality, it would be an R value. Its value is getting pulled out. But when you use star P, it can be used to assign to the box that P points to, or you can use it to extract the value from the box. So it's either an L value or an R value. So this thing is saying, use the address P, dereference it to talk about the box that address is for, and stuff 6 into that box. So now, what is the output? So what does cout x produce? Be brave. 6. It's the value that's in, x's value is in that box, and you used a different way of stuffing a value into that box, different than saying x equals 6. You used this way, star p equals 6. But it's equivalently changing the value of x, which is stored in memory at some location. So you remember when the CPU wants to know what the value of x is, it sends the address for x onto the data bus, the address bus, and back on the data bus comes the value that's in that memory location. So back from that comes 6. Okay, so what's output? 6. And then what happens when I output p? When I see out p? 6? What is p? P is an address. P actually lives someplace in memory as well. That's weird. It has an address. We could take the address of p, and then we'd have a pointer to an int. Right? Because this value, which is exactly what p is, that value, 0x0 ... is what's going to be printed when you see out p. The 0x at the beginning tells you that the number that follows is a hexadecimal number. So that's what is output by cout p, but p itself lives someplace in memory. P is a variable, just like x is a variable, and so it has memory in which it's stored. So someplace in memory is this value stashed away in a box that's labeled p. And we could actually take the address of that box by taking address of p and get a pointer to that pointer. So this comes up in a little bit. Everybody okay? Pointers are just memory addresses, but when you have a pointer that's designated by a variable like p, that variable also lives in memory someplace, and it also has an address to it. Yep.
Just thinking that the ampersand is like it gets you the reference.
It gets you the address. Yeah. Okay. Yeah. But it's a little bit of a confusing operator, because if it's in the declaration of a function, like you say, this parameter is int ampersand x, it means pass by reference. So it's not taking the reference of x, it's saying that the value that's passed in is going to be passed by reference. But in the use like this, do you remember this? You remember? Well, no? A little bit. Don't worry, because it's coming up. We'll see it again. Pass by reference. That's the other use of this symbol. This ampersand is a pass by reference. And in this case, it's actually a give me the address operator. Give me the address of x. Okay, so now the last thing is, everybody can do this in like 10 seconds. Write a statement that outputs the value of x using the variable p. So we're going to output cout, and it's going to output the value of x, but we want to just use variable p. What would you do? I'm typing a letter. Quick, tell me, which letter do I first type? Ampersand. Okay, we got one ampersand. Anybody else? Star P, ampersand P. Which one of those two do people want to vote for? Ampersand P. Even the person that said ampersand P? Okay. Star P. Okay, it was star P, right. Ampersand P would be the address of the variable P. Star P is the thing that gives you the value at the pointer P, that P points to, the value that P points to. So this is what, we don't want that. We want this. Cout star P. Yes?
What if we just put P?
Oh, what if we just put P? Well, like this?
Yeah.
What would we get?
No.
Yeah.
Okay.
It would look like 0x00 something 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 7 or 9 or A. Something weird. It's like a big number. Yep.
Like, if you print out P and print out ampersand P, those are two different addresses.
Correct. If you did this, if you cout, if you cout ampersand P, you would get not 0x0 you'd probably get something like 0x0 BC9. I made that up. But, you know, it's some other memory address where the variable p is stored. Yeah.
For p equals ampersand x, does p get the address of x?
It gets the address where a variable x is stored. Correct. So you shorten that to say address of x. Yeah, cool. Dangerous. It's dangerous to be able to do this kind of stuff. Right? It's like messing around with memory. Yeah.
Is the type of the variable stored in memory too?
No. It's not attached to the quantity that's in memory. But the compiler knows what it is. So it creates machine code that knows that what you're referencing is an int as opposed to a long. And so it knows how much memory is allocated to that and how much to read when it compiles the code. But the code doesn't annotate the data in memory with a type. This is unlike some other programming languages that do that. It just knows on compilation, which means, in fact, you can cast pointers to point that are normally, like suppose you say, I've got this pointer to an int, but I'm going to tell the program that it's actually not a pointer to an int, it's a pointer to an animal data structure, which has many, many fields in it. Then the program will perfectly try to try to understand what's in that memory as a lion or a tiger or some sort of weird animal. And it can get very confused. Okay, that was the easy stuff. Now let's go a little bit harder. So more fun with pointers. Okay, now you know lots of stuff, but the one thing that maybe is maybe new is new. So this statement here, p equals new int, this is something that allocates memory for an integer. This new call allocates memory for an integer from a region of your memory which is called a heap. So it allocates heap memory for an integer. This is like when you're running the program, sometimes when you're running a program, it's necessary to create new data structures, and those data structures have to be put in memory someplace. And the new operator is the operator you use to create that memory for using for your data structures. So some variables, like on the previous page, the variable x, for example, is a local variable to a procedure. Local variables to procedure are allocated on the stack memory because that particular procedure that you're executing is part of the call stack, and the call stack is the stack of stuff. And we'll talk about call stacks in a little bit. But we have this stack of stuff on memory here. There's also this big amorphous heap of stuff over here, this big pile of memory over here. This declaration, as a local variable, allocates on the stack in the current function frame, the scope of the current function. This allocation inside of a program goes into the heap and allocates memory. Why, you ask? Why doesn't everything just allocate off the stack? Or why doesn't it just allocate off the heap? Or why, blah, blah, blah. Why? It's very, well, you could do it the other way. But the reason is because when you're running a function, for example, and let's suppose that function is recursive, and it declares a variable x on one invocation, and it declares a variable x on the other invocation, those two x's have to be different, because the function invocations of the recursive function might change x in one recursive invocation and not in another. So you want something that's like a stack, because you want each call of the function to create its own chunk of memory that it's going to use for its own local variables, and they're not going to be all messed up. This memory, this memory here, that's like permanent memory. It's independent of the function calls. So if you, for example, allocate new memory for some variable when you're in a function, and then you return from that function, that memory is still there. Whereas all of the local variables are gone when the function returns. So it's useful because you might want some function to set up a data structure and then another function to use it. You don't want either of those to be local to one or the other of those functions, right? There has to be some sort of global thing. That's why you use new. Okay, so now we've allocated heap memory for an integer. Both of these things, and when new allocates that memory, it returns an address to it. So P is an address to the newly allocated memory. So it returns, that's an R. It returns address of the memory that's allocated. All right, and now, so here we have some chunk of memory. It's got an address like 0x something something whatever, 7. And P is equal to this, the newly allocated chunk. Now Q comes along and Q is set to be equal to P. So now we have Q is equal to P. So in our picture view of things, we have P that's pointing to this and Q that's pointing to this. They're both pointing to the same memory. Okay, so now you know everything. Now you can, what is output by this statement cout star P after I set star Q to 8? Because star Q is saying that the box that's pointed to by Q should be assigned 8. So whatever that contents of that memory location that Q is pointing to gets assigned 8. And well, it just so happens that we have 2 pointers pointing to the same memory location, and we can access that memory location using P as well. And so when I output star P, that's dereferencing the address P. It's telling me what's located in memory location P, and that thing is 8. Okay, then we create a new int, meaning we create another box. And we no longer have Q pointing to that. We have Q pointing to this thing. And then we set star Q equals 9. So we stuff 9 into that box. And then remember, Q is something like 0x da-da-dee-da-da-dee-da 9 or something weird. And now we allocate P to be null. We say P is null. So what this does is it changes the value of P from being 0x da-da-da-da-da 7 to being 0. Null is 0. Do you like this?
No.
Who said no so emphatically? You don't like it. Why not?
Because you have a memory leak if you do that.
Yeah. Is there any way to get to that number 8 that you've cleverly stashed into that box if you're giving away the only pointer that you have to that memory? Just erasing it? No, you can't get back there. If you set P to null, no, we don't like this because that means that we have no way to access that memory anymore, and that memory is a memory leak. So that's what this is. A memory leak is a situation where the program can no longer access allocated heap memory. Allocated just means that it's been assigned to your program. Your program has been given this space right here that's pointed to by P. It's been allocated for your program, and now your program says, well, that's all right, I'll just forget about it. I don't have any way to get there anymore. Yep.
Can that date ever be overwritten? Like if your variable can its address be to the address that's as a stored and corrected?
Oh yeah. Yeah, the question is, can you ever overwrite that memory location? Sure. If, for example, you had a pointer to the memory location right before it, and you added 1 to that pointer, then you would have a pointer to that, and you could overwrite it. Yeah. So there's lots of nasty things you can do with pointers. They can get you in a lot of trouble. So we don't want to lose access to that memory. And if we do, then that's a memory leak. Do you guys know about, I'm going to write this down because you probably have never used this before. This is on the undergraduate servers. It's a function that you type at the command line. So here's your little command line prompt. And you type valgrind or valgrind and the name of your function, which is sort of like, let's say, / my program. And valgrind will run your program in a sandbox, meaning in a special controlled environment, and it will check to see if your program leaks memory. So at the end of its execution, it will give you a list which says, here's all the bad stuff you did. You didn't clean up after yourself. So anyway, that's a good thing to know about. And you can learn all about it by typing it into Google. Yep.
So we're allowed to upload our PA onto the server through that, right?
No, I'm talking about our servers.
Yeah.
Yeah, in fact, you have to upload your programming assignment onto our servers because you have to check that it works on our servers because that's where we're going to check it. And if it doesn't, then you're in trouble. Or you're not in trouble.
How we check our. Yeah.
There's one way to check for memory leaks. There are many other programs for checking for memory leaks, or there are at least a few of them, and you can use those as well. There's stuff for Windows as well that will check for memory leaks, but I've never used it. I've only used Java and something else. Okay, so memory leaks are bad. It basically means that why is this bad? Why are leaks bad? Why don't we just not worry about leaks? Yeah.
I'm just wondering, so like the A will always exist even after the method ends?
Yeah.
So then if you have like multiple memory leaks, it's gonna stack up and then it's gonna fill like a box with like a bunch of A's, and then you can't use as much of the box.
Yeah. Like think of your memory allocation, the memory allocation system, the thing that's giving out these chunks of memory to your program, it's given out that chunk with the 8 in it. That's gone. Nobody else can use it until it's been deleted. And that memory has been freed. So if you delete, before you set P to null, if you did delete P and then set P to null, then that's okay. That tells the memory management system, that tells the system that gives out memory that this can be used again. But if you don't do that, it's allocated. And it stays allocated forever. Well, until your program stops. And if you're doing this again and again and again in a really nice tight loop that's very efficient, it will fill up all of your memory. And you will end up crashing with no memory. Or it won't, because it won't quite fill it up, but it will slow things down quite a bit. Because now all of a sudden you have to get memory over there and over there, and it's not like nice chunks of small pieces of memory. It's just too big. So that's why memory leaks are bad. They fill up your memory, and then your program crashes. This is a more principled way of dealing with things. This delete call right here will free up the memory. It frees up memory pointed to by Q tells the memory manager, I don't need this anymore, you can delete it. And then it sets Q to null. Do you like that? Yes, you like this. You do. If I didn't set Q to null, what is Q? It's called a dangling pointer. So it's called a pointer that's pointing to memory that's been freed. It's been deleted. It's free. Yeah.
Why does it delete Q and not delete star Q?
Because star Q is the value 9. And the delete system needs to know the address that you're actually manipulating with delete because it's the memory manager and it has lots of 9s inside of it. You can't like say, okay, maybe it meant this one. By telling you the memory, it knows exactly what it's got to do. Yeah, so if I set Q to null, then I have no risk of accidentally re-accessing the memory that I've deleted in this previous delete step. And that's a good thing because it might be that that memory has been reallocated to something else while I wasn't looking. And when I try to get back to this number 9 using my Q pointer, it is now no longer 9. It is something else, like the first character of elephant, because it's been allocated that way. Who knows? And you're thinking, well, I didn't write anything about elephants in my code. But you're on a shared memory system. Who knows? Maybe there's some other thread that you're running that has access to that that's doing elephants. I don't know. Could be. Probably not. But it might be. So anyway, it's a good idea to do this. This is good. Yes. So you might say, well, what if I did it in the reverse order? What if I delete a null pointer? Nothing happens. If you delete a null pointer, that's a no-op. The memory manager is smart enough to know that nobody ever allocates memory at memory address 0. In fact, it enforces the fact that nobody allocates memory at memory address 0, because otherwise you wouldn't be able to tell the difference between null and something pointing to some real data. And dereferencing a null pointer is bad. If you tried to say something like, after this step, if you tried to say star Q equals 10, Q is 0. It's a null pointer. Star Q is supposed to be extracting the location, it's supposed to be referring to the box that's indexed or addressed by 0, and that's not legal. You can't dereference 0. So it would say segfault, short for segmentation fault, and dump your core, or maybe not, depends. But segmentation fault means you're accessing memory that's not allowed. You don't have access to that memory. Yep.
Can you destroy Q instead of having it like just like draw these variables once you created it?
I don't know what that means actually. Because when you're executing this code, Q has been allocated, and then you have this variable Q, and you're saying I want it to be no longer possible for me to touch Q.
Just like have it point to nothing. Like,
Well, that's exactly what we're doing. Setting Q to null means it points to nothing. But actually, it's not possible to say turn off Q in some fashion, other than by doing something like this. Yeah.
Sorry, why would referencing Q in this situation give us 10?
No, this is a statement. This is a statement that I've just added to my program. And I'm telling you that if you added that statement to this program right here, after this null, if you added it there, your code would crash and it would print segmentation fault. Yep.
Saying that star q is equal to null the same as delete q?
No. Saying star q is equal, no. Saying star q is equal to null is setting the pointer, what is q?
It is 9.
No, q is a memory address. Star q is an integer. So saying star q equals null is setting that integer to 0. So it would change this 9 into a 0. But they would probably warn you about this because it would have to type convert null into an integer, and probably the compiler would say, do you really want to type convert null into an integer? And maybe you do. And then you could say star q equals null. But it will not delete. It will not perform delete. Delete is a function call. It has to go to the memory manager. It has to be an invocation in the operating system that's operating and running your program. It has to be told that you're not interested in that memory anymore so that it can put that memory back into the list of memory that's available to be allocated. So your program is not the only thing that's running on a computer. Right? There's an operating system that's there too. And it's trying to make your programs run nicely, but occasionally it has to do housekeeping. And this is one of the housekeeping things that it has to do. Otherwise, you run out of memory. So you have to make a call, which is a system call, and this is a system call, delete. Yep. Do I just say q equals 9? Okay, I could do that. Like down here, I could say q equals 9. Yep. And now you have an address, a pointer, which is supposedly a pointer to an integer, which is pointing to the integer that's located in memory location 9. I have to tell you that memory location 9 is not part of your memory space, for sure. The small values are never given to anybody. But if you put in a different number, like 1,827,300, you could get lucky and you could actually get a number that's in your memory space, and then you would be saying q is pointing to whatever's in that memory location. And then you could go and you could change it. You could say star q equals 7. And then you would watch your computer explode. Potentially. No, it wouldn't explode. But it would be, it could crash your computer. Okay, good? All right. This is all the warm-up to getting to linked list, link structures. So this is a node structure for a linked list of nodes. So a linked list is a sequence of structures. In this case, they have 2 parts. So this declaration is telling you what a node is. It's saying the first part, there's data. So there's data. That's a D. And then there's another part, which is called next. And this is a node. Now, a struct here, that's just a class. Okay? So it's the same thing as a class. Classes and structs. Structs, there's small differences that everything in a struct is assumed to be public, and everything in a class is assumed to be private unless told otherwise, but they're the same. So in this struct, we have a field for data, which is of type lit. So now I have to tell you about templates. So you can declare a particular struct or a class or whatever. You can declare it for a variable types, different types, by using a variable here. This is now a templated class. You can use this as a variable type. So you could make a a node in which the data is a string, and then you would say node string let's call it n. This would declare node n, who is a node that takes as data a string type. Or you could use a different type like node int r, and r would be a node that has an int as its data. This is just like a variable name for the type that's being used in your structure. Okay, so data is whatever type lit describes, an int or a string or something else. And then this is the interesting part. I mean, it's all interesting, but this is fascinating. This is the part which says, inside of my node structure, there's a field called next. And what is next? Yeah. It's a pointer to a node. Whoa, that's recursive. So like I got a node, and inside there's a pointer to a node. And then inside of that, there's another pointer to a node. They're all, so how do you draw this? So you can draw it like this. Next is a pointer to another node thing. And inside of that other node thing, there might be a pointer to another node thing. And now you sort of get the idea why this is called a linked list. And it's a list of nodes linked together by this next field, which is a pointer which is getting you from node to node to node to node in the linked list. Okay. Finally, this is the constructor. This is the recursive pointer reference. It's a reference to a pointer to another one of these structures. This is the constructor for a node. It takes some type of data, and it takes a pointer to a node, P, which this is saying that the default value, if that is not supplied, is null. So this is saying there's a default value if I construct something and I don't provide a second parameter to the constructor, it just assumes that second parameter is null. And then what happens is it uses this initializer list to initialize the data to be D and the next value to be P. And now I've constructed a new node with data D and next value P. So if I wanted to create this picture here, the first one, this, I would just say head equals new node int 8, comma, well, if I wanted to be, I could just do this, because by default it'll be null. That thing right there is null. Does this make sense? It's like a combination of weird syntax, like this whole angle bracket lit thing. It's kind of weird. Weird syntax, and the ability to manipulate memory at a very low level that makes C++ a challenging programming environment. Yeah.
Does it all have to be the same type of data? So in the last line, if you replace another type instead of it, you use something else, would that still work?
Well, this is a good question. In fact, I actually, before I came to class, I was thinking to myself, I think it defaults to lit. But right here, I don't actually explicitly say that this thing is a pointer to a node bracket lit thing. But I believe that that's the default. And so it would be a chain all of the same type of thing. But I could be wrong. And if you want to make a list of multiple things that could have multiple types, then typically what you do is you create a superclass that contains all of those different types of nodes and call it like the supernode. And then you'd have a linked list of supernodes. And each one of those is a special type of, there's subclasses of that are going to be of a particular type, like int or string or whatever. Yeah, but it's a great question, and it's too advanced for me. Yep.
So why are we using a new?
Why? Because I wanted to allocate it off the heap. Why did I want to allocate off the heap? Well, probably because I'm creating a linked list that I want to give to somebody else. And if I created it on my own local stack, my own local memory chunk that's on the stack space, then when my function returns, all of that stuff is gone. All of that memory would be gone. Yes?
Also, for the template, could you briefly go over again the difference between like what the class name and what the name between the angle brackets represent?
The name between the ankle brackets, that lit, is just like a variable name. You could have named it dummy. You could have named it, I don't know, type. Sometimes it's used, T is often used.
And then for a class, it would be like a primitive C++ type or like a struct that we define.
Yeah, it's like a class or a struct or something within that templated realm. Yeah.
Is int in the angle brackets replacing lit?
No, int in the angle brackets is replacing lit. INT.
That's replacing lit.
Correct.
Okay. Could we have just wrote int d instead of lit d there?
Sure, we could have, except that that wouldn't apply to any other.
I see.
In fact, it would have been sort of a pointless use. We shouldn't have used lit. We should have just declined it. We should have just defined the linked list to be a linked list of integers, which I am not against. And frankly, I'm slightly against templates. They make things crazy. And if you programmed C++ years ago, when C++ was just a macro language that sat on top of C, all these templated things were unrolled into, like, for every type, it would repeat all of your functions again and again and again, just with a different type. Again and again. Now it's smarter, but it still makes me nervous. Yeah.
So template pretty much means any variable. Any variable type can be.
Any type can be used. Any type can be put into that. So you could make a node of, I don't know.
So even if, like previously I defined, I made my own class.
Yep.
Say like card, and then I have like fields and then car color. So I can also use card.
Yep.
No?
Yes. Yes. Yes.
Oh, okay.
Yep is yes. Okay. How do we do this? How could we have only gone through 3 slides today? That's not possible. How do we do this? Quick. We have to do it after we did this thing. What do we do? Quick, tell me what to write. Head equals new node bracket int bracket parentheses 6 comma head. Very good. Excellent job. Okay. Now look. Don't ask a question right now. It's a very bad time because I have to turn the page. See, we didn't even get to that. Okay. We'll get to it. Now ask your question.
Also, when we were creating like the second node, when we were passing in head, should we pass it in as like an ampersand head?
Nope. We should not pass in head as ampersand head because that would be the address of head. Head is a variable. It lives in some space. That is not what you want. You want actually the pointer to the node, which is called head. Yep. Maybe. Go ahead. All right, I'll see you on Wednesday, and we will go faster.